Mhm. Okay, so hello everyone, and welcome to the talk on the techniques to read the Dotty code base. So today I would like to share with you some techniques that I use when I read the Dotty code base whenever I need to analyze an issue to fix an issue. So ever since I came to EPFL, I have been interested in the topic of how to read the Dotty code bases. Because that you need to do when you are fixing issues, and we have the amount of issues constantly creeping up, and that ties into the subject of sustainability of the language. So in order to be sustainable in the long run, the language needs to have a mechanism to transfer knowledge from previous generations to future generations, so that people so that enthusiastic people from the community can also come and help out with issue fixing. So that's why I have been interested in the subjects of how to read the Dotty code base. And first of all, I wanted to show you the techniques that I was using until very recently to work with issues, until I found these techniques that I'll show you a bit later in the presentation. So the techniques that I have been using in my first months, in my first years at EPFL as a compiler engineer is what I call the hopping causal chains. And the technique is that, okay, you have an error that happens somewhere, and this error is triggered by some line in the compiler code that says the compiler to emit the error. And that line itself is a result of the compiler taking a certain branch in the control structure that the error belongs to. That is an if statement, for example, like if a certain flag is not set, then emit an error. So in order for the error to be emitted, that certain flag needs not to be set. And then you can ask yourself, okay, why does that happen? That also must have a certain cause. And the cause of that cause must also have a certain cause, and so on and so forth. So everything has its own cause. And the idea is that you start from the site where the error actually happens, and then you follow the causal chain, all the causes. And the idea is that if you do that for long enough, you're going to come to the place where the root cause is, where the actual mistake in the compiler logic is. Then you can fix that, and the error will be fixed. So to demonstrate what I mean by this technique a little bit more concretely, I picked an issue that was that is no longer an issue. It is already fixed, fixed by Dale, by the way, who is here also. But we are going to look at it anyway because that's the ones that I picked for the talks. So it's a spurious unreachable warning. It's a match on an IDT issue. So what is that all about? So we have a certain code. We have a certain enum here with two cases. And one of the cases has a Java object as a member. And then we have a function. And the function does a pattern match on the two cases. And the thing is that it reports that one of the cases is unreachable, even though it is reachable. And even more weirdly, I minimized it to this format. So no enums, just one case class. And it takes Java object, Java, well, once is an enum, so Java enum. And then we have a pattern matching on inside the function on this case class, and it still reports unreachable case warning. So if you look at the actual reproduction of it, if you try running the code, you're going to get the unreachability warning, unreachable case. So you get a warning like this. So obviously it's not correct. And
Totally. What was the
yes.
explanation in the issue for this? It's something about space.
Yeah, but we will get to that. I mean, the idea of this presentation is that you come to it with zero knowledge of the code base, and then we are going to dive into it together to demonstrate the technique.
Got it.
So we are going to get to why exactly it happens, but in a more like systematic way. So the way you might be debugging, the way I was used to debugging this kind of things via the jump in the causal chain method is, well, first of all, you find out where exactly it happens in the compiler. And to do that, you might want to, for example, copy the error message, and then you might want to go to the compiler sources, and you might want to search the compiler sources for the warning text, and you might get the result. And you might see that the unreachable case message, it actually is embedded in the class of the same name, match case unreachable. And then what you might want to do is you might discover where that is used from. And if I had my metals working, I would be able to ask metals to discover that. But you'll have just to believe me that it comes from, okay, it works. So you can ask metals to say where exactly it comes from. And you will see that it comes from the space file, the space.scala file, and what this file does and how exactly it works, you may not know. And that's the entire point, that to fix the issue, you will need to know how it works. But you can already trace two locations in this file where exactly this happens. And then what you might want to do is you might want to inject the println statements to see which exactly of these cases get executed. And what you will find out is that this one gets executed if you inject like print A here and print B next to the other case. And then you're going to see that the case inside the for loop gets executed if my compiler doesn't hands now.
What version is this?
That's the older version. I deliberately reverted it by like 10 days so that it still is an issue because I know that it is fixed.
Yeah, but the deferred part, I think.
The deferred part, what?
Yeah, that deferred part, that's being gone. Oh, maybe I'm misremembering. Anyway, okay, fine. Sorry.
Yeah, it's from 5th May, so at least on 5th May, it's been there. Well, but anyway, probably not a good idea to wait for this compiler to compile everything with Zoom open. So you can just believe me that that's the line that gets triggered. The point is that to what I was used to doing before is I was trying to understand why exactly this line gets executed by analyzing the code before it. So, for example, if this warning on this line was emitted, then probably the loop was executed. So this for loop was executed, and for it to be executed, the collection that it iterates on must not be empty. Yeah, right. So we have here the output, and we have here the A that was here. So in order for the loop to be executed at least once, we need a non-empty collection. And before that, we need we see that there is an else statement. So if else, so it means that the compiler here took the else branch, and it tells us that the predicate that it was looking at the if statement, it was false. So one of those two conditions, it was probably false. So then what you do is you analyze why exactly those conditions were false, and so on and so forth. So everything has its own cause, and you jump the causes to see where exactly the root cause is. Now, there are certain problems with this kind of approach, and maybe I'll ask you to say if you see what problems you see with this approach on yourself already. Anyone has any ideas?
In progress.
You can't tell if a behavior is right or wrong is a problem.
Yeah.
So you don't know if you should, find the cause for the wrong behavior, or if that behavior is right and the cause is somewhere else. Like, you just don't know.
Yeah, exactly. Anyone else? Any thoughts? Well, as Dale said, it's one of the things that you do not know. If you do not know the compiler and you're trying to approach it naively like that, you might get like, okay, the collection was non-empty here, but was it supposed to be non-empty, or was it supposed to be empty and that's a wrong behavior, or if you look at this predicate, it was false. So was it supposed to be false? Is it supposed to be the case that either previous should be non-empty or covered should be non-empty? And don't forget that you don't even know what this previous and covered are. You're just naively analyzing the code base. So of course you cannot tell what the correct behavior should be. And so you cannot, it's very difficult to decide where to keep tracing like that. And so you get an explosion of complexities this way. But besides that, I had other problems with this approach. So there are often too many links to jump. So if the cause is located if the root cause is located pretty far from the error, then you need to jump a lot, and also you get these cases where you do not know which way to trace. Should we trace the previous branch of this if statement, or the covered branch of this if statement? Which one is correct? Another problem is that, as we have just discussed, at each fork, you do not know what the compiler should have done. And another problem that I had with this is that it's comparatively easy to trace the logic, but it's harder to trace the data. And the data is what the predicates are, what the if statements work on. It's the objects, it's the trees, it's the symbols. And the reason it's hard to trace the data is because, well, if the data is mutable, if the object is mutable, then you do not know what mutated that object and where. And if this object is immutable, it's not much easier because often okay, it's easy enough to trace where it was created, but when you arrive to where it was created, you might notice that it was actually copied from another object with a slight change. So it's really as good as mutation, and you need now to trace that copy, where that copy was created, and so on and so forth. So it's not that easy. So the lesson I learned from this attempts is that abstractions are obscure, and you need context to understand them. And abstractions is what programming is all about, what Dotty compiler is all about. And the thing is that if you're dealing with an issue, you need some context of where the issue happens, of how things are supposed to work, to understand whether or not a particular piece of code is doing the right thing. So currently, when working with a compiler, I'm trying to stick to a new workflow, which I'm going to talk about next. So the new workflow focuses not on tracing the causes, but on the background knowledge collection. And the background knowledge is the contextual knowledge is the knowledge about things like why a certain piece of code exists, what purpose does it serve, the part of which bigger code base is it, what is it used from, and so on and so forth. We are going to get back to it later. The idea is that the error and the fix often become much easier to find, and in some cases even obvious, once you understand what the code in the general area of the compiler does. So to establish the context that is necessary to fix an issue, I currently work on, I currently use the following technique. So this technique is, I use it whenever I deal with a code base that I haven't seen before, a piece of the compiler that I haven't seen before, and I do not have any knowledge about it. And the question is, how do I establish the knowledge of what it does? And the way I do it is as follows. So first step is to figure out the general area of the compiler that misbehaves. Like for instance, in our case, it is okay. It is the error happened on a certain line of a certain file. So I might look at what the file was. So the file was space, and then I would look at the package of that file. So it's in transform pathmat. And I would look deeper into the context of those packages, like what else is in those packages, and so on and so forth. We are also going to get back to that a little bit later. So once that figured out, the general area, I try to forget about the issue for the time being. So it means that I shift the focus from trying to figure out the why the issue happens from the issue at all. I shift the focus to trying to understand the compiler in that area. And to do that, what I do is I read the entire area and try to understand what it does and in general how it works. So it means if I'm dealing with a file, what I'm going to do is I'm going to read it from top to bottom, one line at a time, of course, skipping stuff. I mean, if the file has like 965 lines of code, I'm not going to read every line. I'm going to read it on the missed level, for example, and I'm not going to understand it maybe at all. Maybe I'm going to understand it by a degree of 20%, and it's already good enough. So so I get at least some context knowledge about that file. And once I read it and understand even a tiny bit of it, not all of it, even a tiny bit of it, what I'm going to do is read it again with a little bit more of the acquired context. So anyone, any idea why reading the file again might be a good idea? Anyone, any opinions? Well, the reason I do it is because with every read, every iteration of going through the code base, I acquire a little bit more of the context. And with that context, I can understand a little bit more of the stuff that I didn't understand. So it goes back to what I said earlier, is that to understand abstractions, you need a context. And with every read of the code base, you get a little bit more of the context.
Totally. Do you want questions as you go along, or do you want people to wait and
yeah, sure. If you have a question, go ahead.
One of the things that I always want is the ability to see the AST and to see how it changes across different lines of code. Is that something that's part of your process?
No, I mean, that's something that I would very much want myself, but that goes back to the topic that tracing data and data changes is hard. And so far, I'm not aware of any debuggers that would show you how an AST changes and what changes AST. So well, unfortunately, I'm not aware of that.
Well, there's vprint, which prints tree changes across phases, which is super useful for that.
That sounds useful.
Yeah.
So, I mean, did you discount that, or do you, were you not, did you not know about that one? I'm not sure.
Well, I assume the bprint is does the same thing as xprint, right?
Yeah, bprint.
Similar thing, yeah.
No, it's exactly the same thing. It's just different alias.
Yeah. So what I meant by difficulty to trace data is like, okay, in that specific case, you can trace how the entire compilation unit is changed from a phase to a phase. But what if, for example, you want to trace a single tree or a single symbol or a single some other object and know where it was mutated?
Mhm. Yeah, you need to minimize it small enough so that
Yeah.
like, the entire compilation unit is the tree that you're interested in, ideally. And to do that, separating sort of auxiliary code from the specific tree that you care about by sort of compiling into parts is super useful. That way you can, xprint only sort of use site code rather than like utility classes or whatever. And then you get, and I think you can, well, also there's a part that it diffs, any changes in phase that, any phase that doesn't make any changes, aren't part of the output. So it's nice and minimal. But of course, that's at the phase granularity, and that also includes any mega phases that fold mini phases together, which, I mean, I've never had it as a problem, but potentially could be a problem, which, yeah, anything within a phase is doesn't have a similar facility.
Yeah, exactly. So that's why I have this workflow to try to understand stuff on the phase level, because there we do not have this. Well, not only in the phase level, also across the phases, it's also good to understand how exactly stuff happens, because you might get the AST output from one phase to another, but you may not have a very good idea why exactly that changes. So yeah, this workflow is more like less technical and more reading frameworks that I'm trying to show you. More reading oriented. It's more oriented on how to read the code and less oriented on how to actually execute and interact the code. So acquiring as much context via reading the code as possible. Yeah, the idea is that you read the code a couple of times, the code of the general area that misbehaves a couple of times, and every time you accumulate a little bit more of the context. And only after that you get back to your background, back to the issue, while having the background knowledge. And the idea here is the same, that once you come back to the issue with the context, you understand it a little bit better. And one caveat that I found, why do I try to stick to the technique pretty closely? The technique that I'll show you in the next slide, why I'm trying to stick on it pretty closely, is because I found that very often when dealing with unfamiliar code bases, the intuition may be misleading. So what that means is you may have an insight on how the issue fixes, what triggers the issue, but that insight might be wrong, and you might follow that insight prematurely. So what I try to do is I try to first collect as much background knowledge as possible before following any hunches or intuitions on the exact cause of the issue. Because if you follow the wrong intuition, even though it is tempting, then you might get into a rabbit hole and waste some time chasing stuff that is not the cause and that shouldn't be considered. So now the question is, so I was talking a lot about understanding and reading the code base and the techniques that I used to read the code base before getting to the issue. And here is the exact techniques that I used to read an unfamiliar code base that actually worked pretty well for me whenever I followed it closely. And this technique consists of 6 questions. So 6 questions that I usually ask myself about a chunk of code that I have never seen before, and that is located in a part of the compiler that I have never seen before, and that I have no clue what it is doing. And to answer those questions, it's you can use either reading the code base, or you can use flags that we have just discussed, the xprint, the bprint, the analysis of the trees, the minimization of the trees. So all of this can be used to collect the information to answer you about the code that you're reading. So the first question is, what hole does it belong to? So the idea is that compilers and programs are big machines, and machines, they consist of certain parts. And every chunk of code that you're reading, it will be a structural part of some bigger code with some more abstract and more general purpose. So you would need to do it. So what I'm trying to do is to determine that first. For example, there is an inliner. Yes, there is an inliner in the compiler, and you can say that, well, an inliner is a part that implements the inline feature. So what you can say is that inliner is a part of typer. Then to check your reasoning about determining the place of the component in the bigger picture, the bigger organization of things, I would ask myself, what features, why do I think that it is a part of the typer, of that whole? Like what features make it a part of that whole? And for the inliner, we can say that because it is used from the typer phase, we say that it is part of that of the typer. And by the way, I'm going to give you first all the questions that I ask, and then we are going to apply them together to the code base in question to see how they work in practice. The third question is that I usually ask is what are its features that differentiate from the parts from other parts of the whole? So the idea is that inliner, for example, is not the only piece that makes up the typer. There is also other stuff in the typer, but it might be good to see how the inliner or any other piece of code that you're analyzing is different from the other structural pieces of where it belongs to. And you can say that an inliner lives in its own file and contains functions that expand trees. So living in its own file is pretty important for something that is a part of a typer, because usually the typer is pretty self-consistent. It's one big file. So inliner got its own file. So for starters, it's good enough to say that it lives in its own file. Once you have those three questions answered, it might give you already enough context to answer about the purpose of the chunk of code that you're analyzing, because where it belongs in the bigger structure of things, it's already a good enough indication that might give you enough context to try to establish the purpose of this thing. For instance, an inliner's purpose is to enable the inline language feature. And to establish that, you might need to look to read the inliner's file from top to bottom, the way I described previously, maybe a couple of times to establish the context. Once you have determined the place of the chunk of code in the bigger picture of things, you now may start treating it as a world of its own, a machine that consists of other pieces. And you might even want to start doing that even before you get to the purpose of the chunk of code, because it ties very deeply to purpose, to analyze what it consists of. So you're breaking it down to components, and you see what it consists of and what parts make it up. So for instance, we can, if you look at the inliner file, we will see a bunch of methods. We will see that some of them are public, some are private. And also we will see a bunch of vars, the local mutable state. So next, the final question that we are going to ask is about the governing principle between all of its parts. So the point is that if something belongs to the same whole, then probably it has something in common with other parts of this whole. And figuring out the common pattern between all the parts of a machine might give us some insight about the purpose and the logic that drives that machine. So for instance, for inliner, we would see that, like, for starters, methods take trees and spit out trees. And not only that, they also, all of or almost all of these methods they expand trees. So take a tree and expand a tree. And also we will see a bunch of utility methods that examine trees to determine something. So that's 6 questions that I just try to answer no matter what, without trying to divert and follow any hunches if I don't understand the code base, because they provide some, at least some contextual knowledge. Not all of it, you still will need to dig into the code base and follow your intuition, follow your hunches, but at least those 6 questions already give you enough platform to at least alleviate alleviate your work on the code and allow you for better quality of your guesses. So that's that. And now before we go and try to see how those questions work on the actual code base, maybe you have any questions about it, any thoughts?
The one question I have is somewhat irrelevant, in the sense that I'm desperate to know when there'll be a version of the compiler that's debuggable in, IntelliJ or VS Code or Emacs with metals or Vim with metals. I know you laughed, and I know it's a hard problem, but is there a plan for this?
I'm not sure if there is a plan for this, but that's definitely something that we are aware of. That debugger doesn't work on the compiler. I guess that Toolin's team would know better, but no plans that I'm aware of. And I guess that would be even tricky to implement because like the compiler, it has complicated flow of logic. There are loops, there are recursions, there are, well, the same piece of code may be executed a bunch of times, a lot of times. And if you put a breakpoint there, it might not even give you the clarity that you want. Okay, so if there are no other questions, maybe we can try using this technique on the sample issues that we have just described. So one caveat, one thing before diving into the code is we are going to jump the levels of abstractions here. So it means that we are going to start maybe with the line that triggered the error. Then we are going to widen our scope of attention to a wider area. And then we're going to work on that wider area, trying to understand that as a whole and forget about the line until we understand the area. And another caveat is that, like another disclaimer, is that we're not going to be tracing the issue until like completion, because to actually understand the few parts of code that are involved in the issue, it will take some time. But we are going to try to understand the pattern matching area and to make a point of reading the pattern matching area and try to understand a little bit of how it might be contributing to the issue. So we are starting with the warning case, the line that triggers the warning, the unreachability warning, and it is located in some files that you have never seen before, and it's the files that you don't even know what it does. And the objective is to understand the piece of the compiler that triggers this issue. And to do that, we can start going through those 6 questions that I indicated to establish some context. So first is what is that whole that it belongs to? So this line of code. Any ideas, anyone?
The space engine.
Well, yeah, the space engine, but you're the one who fixed the issue, Dale. So of course you know this.
I mean, I gave
What?
time. I gave time.
Yeah, you already read this code base. So
I can't answer.
What?
Never mind.
Yeah, okay. Well, so okay, if nobody has any ideas, nobody of those who sees this code base for the first time, the way you can reason about it is that first of all, this line of code is a part of a certain method, the check redundancy method, and that method in turn will be a part of a certain object or a certain class. And if you look, it's a class, it's a space engine. And that space engine in turn is would be a structural part of the space.scala file, which in turn is a part of a certain package, which is transform patmat package. And you can have a look at that, where that transform patmat package is located. And you see that it only has this one file. Another thing that you can do is to determine what does it belong to, the part of which whole does it belong to, is to see where exactly it is used from. So if we can use metals to find all the references to the symbol. So if you do that, we see that it's used from a certain file called pattern matcher. And if you look at that file, you will see that it contains a mini phase called pattern matcher. And then you know that this space thingy, it's part of a pattern matcher mini phase. And then you might want to have a look at where this mini phase is in the context of other mini phases that are being executed. So you go to the compiler, which has all the mini phases, and you look up for the pattern matcher. So you see where it is executed. You see that it is one of the transform phases. It is executed after the typer, after the pickler, and apparently has to do with the pattern matches, and judging from the name. So you already established a little bit of a context for this scene. And next, once you have established the bigger picture, the place of the file in the bigger picture, it might be instructive to switch the attention from the actual issue side to a proper level of granularity, proper level of abstraction. So if you look at the issue is that there is an unreachable warning that shouldn't be there. And unreachable warning is a part of the pattern matching logic. So maybe a proper level of granularity would be this space file to look at. Why the space file? Well, because if you look at the pattern matcher, you will see that it mostly relies on this space engine to do its work. So technically, we are looking at the pattern matcher phase by looking at this space engine scene. Does that make sense? So then we can, what we can do is we can, well, what features make it a part of the whole here? It's the question is pretty irrelevant because we have already established that it's structurally part of a certain file and a package, and it's used from a certain mini phase. So it's that's why it's a part of that mini phase. Next question is, what are its features that differentiate from the from other parts of that whole? If we are talking about the space engine and the pattern matcher being a part of the bigger compiler, then how exactly the pattern matcher mini phase is different from the other phases of the compiler? That's the question. So you can say that it's different from the other parts of the compiler by the virtue of its purpose, which is other question. So from the name, from the comment to the file, we see that it's supposed to be dealing with pattern matching. So it has a special purpose, and that's one of the differences. Another feature that we might want to consider is that this pattern matcher phase, it actually lives in two files. So pattern matcher and the space lives in its own package, and it's the only file in that package. So that's also a piece of context knowledge that may or may not be useful. Next, there will be a question on its purpose and what it consists of. And to answer that question, you will need to read the file and to read it the way I described previously, from top to bottom a few times, while trying to understand what exactly it does, and maybe not understanding everything, which is okay. So what you might want to start with is from the comment at the top of the file. So you will see that after reading this comment, you will see that it describes the theory on how the pattern matcher works from a theoretical perspective. So in abstraction from Scala, you will see that it treats types and it treats patterns as spaces of all possible values that can populate that type or that pattern space. And once you treat those like that, once you speak about the types and the patterns in the same language of spaces, you can answer questions about whether a pattern covers a type or whether a pattern is reachable or not. So, for instance, in this comment, we will see that for the problem of existivity check, its formulation in terms of space is as follows: is the space type of T a subspace of the union of space covered by all the patterns? So union of space covered by all the patterns refers to all the cases that a pattern match has encountered so far. It will create a certain space, it will form a certain space, and then if the space of all possible values of a type is a subspace of that space formed by all the patterns, then we can say that the pattern is exhaustive. So there are no values of the types that are not covered by the patterns. Similarly, we formulate the enrichability problem. So is the space covered by a pattern a subspace of the space covered by the previous patterns? So if we have a case in a pattern match that is already covered by the previous cases, then this case is unreachable. That's what this is talking about. And from this comment, we can also see what's important for this from the theoretical perspective. So it's talking about the existivity check and the unreachability check. So we can assume that these are the two things that the two big checks that the space engine is supposed to do. This space theory is supposed to do. So any questions, any thoughts? Feel free to interrupt me if you have. So once you have read the comment and understood more or less in human language what the file is all about, you can start reading the file from the top to the bottom and analyzing it structurally. So first you would answer the question, what does it consist of? And what does this file consist of? Let's take a look. So we can see that there are some AST-like scene. So there is a still trait, and there are some children of that trait, and those children are case classes, and they look like they are a domain of a certain area. And if you look at them, it's you can relate them to the comment that you have just read, and you will see that they describe the things that are described in the comment. So you will see that there is a space for types, there is a space for patterns, there are union spaces, there are product spaces, and so on. Yeah. So after that, after you have so besides that, besides AST, what we see also is some other pieces of this file, which is bigger traits and bigger objects and bigger classes that contain some methods. So we see that there is a trait space logic. There is a space engine that extends space logic. And also there is a companion object to that space engine sim. So then you might you might infer that to understand the space logic and the space engine, well, to understand the space engine companion, space engine class, you might want to dive a little bit deeper into the space logic trait. So you might want to expand that and to see what it has. And the way you do that is you also try to answer those questions about the structural analysis of the code. So what is its purpose? What does it consist of? And what is the common principle between all of its parts? So what does it consist of? And the common sins between common governing principle between the constituents would help you to determine the purpose of a chunk of code. So what does space logic consist of? So it consists of a bunch of methods, and then the question is what exactly those methods do. What is the governing principle between those methods? So we see that many of them are abstract, and there are not that many actual concrete methods. Only those methods that I highlighted are concrete, and many of them are abstract. So what we are going to do is to read them one by one and to see the pattern between them, the common governing principle. So first is there is this is subtype method, and it takes a type and another type and returns a boolean. And in the comment it says that it checks that the one type is a subtype of another type. So it's pretty straightforward what the purpose of that is. The next one is the same unapply. So it takes two term refs, and then the comment says that it is true if we can assume that the two unapply methods are the same. And so already what we can establish about those two methods that we have just saw, the common governing principle, is that they are both utility predicate methods. So one is used to compare types, another is used to compare the term refs, and they both are utility methods, and you can assume that they will be used from another method. So they're not the main methods. They that contains the actual logic of the space logic. They are utilities. The same we might say about the next method. So intersect and related atomic types. So it also feels like a utility method because it's no longer a predicate, but it's an operation over two types to return a space, to intersect them into a space. Then we have another predicate method, can decompose, that answers a certain question about the type. The question you might not know exactly the purpose of the question, but you know that it is a predicate. Signature, it says in the comment, return term parameter types of the extractor unup, which is an argument here. So it also feels like a utility method. So by the virtue of analyzing the space logic so far, we can already say that it contains a bunch of utility methods. To serve a certain bigger purpose. And then we might stumble upon the methods that are not abstract, the concrete methods. So for example, simplify. And we will see that what it has here is looks very much like an algorithm, because in the Dotty compiler, whenever you see a big pattern match as follows, especially when it involves recursion, you know that probably you're dealing with a more complicated algorithm. So you might want to read the comment what that does. So simplify space such that a space equal to empty becomes empty. So probably at this point you might judge that also after looking at those cases, at what it deals with. So they deal with the AST that we have seen before, this AST. So probably you might infer that if you have a nested a big AST, like a product or an or a union of spaces, that you might want to simplify that to an empty space. All of that you can infer by skimming through the simplify method without going into more details of how exactly it does so. In a similar way, we can continue reading through the methods, but so far we have already inferred enough context, which is that the space logic scene contains utility methods, and also it has some algorithms that serve certain purpose. And the reason why I'm focusing on algorithms is because they're usually the most complicated part in the compiler, and so you need to know which algorithms are in the area that you work in. So the simplify is one of the algorithms that incidentally is important for the issue in question, because the simplification goes wrong. So now that you have understood a little bit about the structure of the space logic, can you still hear me? I think my mic died.
We could hear you a second ago. So.
Sorry about that. Okay, I think. Can anyone say something to?
Yes, we can hear you.
Okay, great. I can hear you too. My headset died. Sorry. So yeah, so once you have analyzed this piece, the space logic, you can then have a look at the space engine the same way. The companion object, this is that it's not too complicated. Contains just actually one overloaded predicate method. That's also a good context to know. And finally, you can, after you have analyzed those pieces, you can go to the final piece, which is the space engine, and immediately see that it has some state in it. So some references to the definitions. So if you see this definition scene, it's referenced actually pretty frequently from the compiler. It's where the symbols known throughout the compiler reside. So that's the references to those symbols. And then it also has a bunch of methods, some of them private, some of them not private. And we see that there are methods that repeat from the space logic, because we extend space logic, so we implement the logic that we have seen before in a certain way. And what's more importantly is that we see that there are two methods called check exhaustivity and check redundancy. Why that is important is because we have some context knowledge by now that exhaustivity and redundancy checks, they're one of the two important operations that are done by the space engine. And now, then we can remember that the errors that we have encountered, the erroneous behavior, it comes from the check redundancy method. So we have came to the same place we started from, but now the difference is that we have looked at the file, and we have the context about it. So when we first came to it, it was just some line of code at some place of the compiler that you have never seen before. And now you can say that it's a line that happens to be in a part of the logic of the pattern matcher. And the logic of the pattern matcher is based on the theory that is the space logic that is described in the comment, and also incidentally has a paper written about it. And moreover, it comes at a place of one of the two important operations that are done by the pattern matcher, by the space logic, which is the redundancy check. And even more than that, when reading through the algorithm of the check redundancy sin, you will start spotting the sins that you have already seen before. Like for instance, like to underline sin, you will remember it from the methods that you have seen. It's the same space engine type that you read, or at the space logic sins that you read. So you will notice that the utility methods that you have previously seen are used in this algorithm, and you will not be surprised by them anymore, because there is a difference that you read an algorithm and you see a bunch of unfamiliar method names, and you can identify which ones come from the same context, from the same file at a glance, and which ones are not. And then you will see also the references to the algorithms that we have encountered that, so I'm talking about the simplify algorithm here. And also I believe the project sin is also one of such algorithms that is one of the parts of the space engine logic. And if you keep diving like that in the specifics of those algorithms, you will encounter that the problem actually happens, I believe, in the simplify method, but we are not going to do that right now for the sake of the lack of time. But the main point that I wanted to showcase here is that if you approach the code base, the line of code that triggers an error, after spending a little bit of time to systematically study the area of the code around this issue site, you will start having a little bit more context about the big picture, where we are at the big picture, and you will start seeing familiar sins in the code, so calls to familiar methods that you have seen previously, and it will you may or may not get some intuition about that. So this information that we have covered so far is not enough to actually fix the issue, but it's enough to go a little bit deeper and collect a little bit more information using the same pattern and come to the cause of the issue. So that was the technique that I'm currently using whenever I'm dealing with Dotty Codebase. That's what I wanted to share with you today. And I don't know if you have any questions or any comments, you're welcome to ask. Maybe you, Dale, want to comment something, because I mean, you're the one who fixed the issue. So you have a little bit deeper insight in that than me in why exactly it happens. If you want, you can also say a few words.
Yeah, well, this one in particular, you know, sort of you diagnosed the root cause, and so then it was easy to sort of go from there and confirm what you saw, and then try and figure out why Java enums in this case weren't giving the right data. But I guess what I wanted to add, see how you can, for instance, also like how you evaluate it now as a debugging technique. Sort of two things, but the ability to like take a small variation of a piece of code that does behave correctly and compare and contrast how that runs through the compiler, with xprint or some tracing or some logging, or like something added to sort of compare outputs is extremely useful. I found it sort of invaluable in very complicated compiler, where you really don't know where to even start looking. It's good to sort of see where behavior deviates between two as close as possible codes. And then there's, in the compiler in particular, there's lots of recursion. But I found the trace utility very useful. at least to get something to start to look at in terms of like, you might get a sense of something occurring in type compare or in typer, or in some other aspect of type mapping, any kind of mapping of a deep structure. But you have no idea which component of it, like what's happening in the general sense. So enabling or adding the sort of logging, the trace logging around methods can be useful. But what I have found, which is a technique related to that, is that some methods are used everywhere. You get some really core sort of method lookup, member lookup methods on symbols or denotations, and adding tracing to that, you might as well stop using a console, because it's gonna be full. So what I have found to be useful, if you can pull it off, is to basically duplicate the method that you want to trace and then trace that one. So like, find method 2 or something, and then wherever in the code base you were calling find method, use find method 2. And now all of a sudden you have sort of context specific tracing. So only when find method 2 is called do you get tracing.
Have you ever considered using a thread local to do that? Have the debugging output conditional on the thread local being set to true, and then only set it to true on the way into the, at the particular call site that you care about. I mean, that's just an idea I'm having off the top of my head right now, but
yeah.
It seems like that might be easier than actually duplicating the method.
Yeah, probably can just mutate a variable.
Recalling the debug sessions that Dale and I have done, it's like it's often the sort of the flow is start with vprint, and then you figure out what phase something it goes wrong in. Then you enable logging within that phase, and then you can sort of see that here it's still correct and here it's wrong. And then you want to, that window of time of like, well, where exactly is it going wrong? Then you start trying to narrow that window, right? So you enable more logging to get more detail within the window of time that you care about, and then narrow it down further. That's a very common workflow, I think.
Yeah, maybe we could make a video about your workflow one day if you are up to. I mean, it sounds like you have a lot of pretty nice techniques that cannot be covered in like 5 minutes. Some of them I know, some I don't.
Yeah, I think what Dale and I could do is in our future sessions, sort of for 5 minutes at the end after we finish, like reflect on well, what techniques did we use today, and then just write them down, and then sort of gather that over a series of sessions, and then maybe produce a write-up that you should use.
Yeah, but also be a great idea.
Yeah. Did you mention git bisect yet?
The question is to me, or?
Yeah.
No, I didn't cover git bisect.
Okay, because that's almost always, maybe everyone knows this already, right? Because some of the stuff is like standard debugging techniques that you use on any code base. But whenever I'm debugging a regression, it's almost always the first thing you want to do is do git bisect to isolate the pull request that caused the problem. So much easier to then at that point the cause has been narrowed down so far that it's often even obvious what the problem is right away, or the sort of investigation space that you need to explore is far smaller. And if you're, and so git bisect in general, right? But then there's like techniques for doing git bisect on Scala versions in particular. We have a script for this for Scala 2, and then I think someone just published. Didn't someone just tweet or publish something about some automation for doing this in Scala 3? Does that ring a bell for anyone?
Well, Nico was going to look at it.
Nico,
but I'm not sure if he's published anything. I mean, I've not seen anything.
That's just a basic thing that any like new contributor should be comfortable doing. You know, should we should try and document that and make that easier.
Yeah. Well, now it's good that we spoke about it, because now I can text that in the YouTube video, and then we can. It can be sort of a summary to be described later. Okay, great. So anything else, anyone?
I'm thinking about sort of, you know, past stories of our debugging sessions. One sort of useful, there's a whole sort of category of techniques which are not about the debugging itself, but it's about sort of attracting the attention of an expert. So like, I'm thinking of this fix that Martin landed earlier today of a bug that had been open for like 9 months, where you could, in the REPL, you could call a method once, and then if you called the same method again, it broke. You know, it was just insane. Dale and I worked on this for a while, like failed to fix it, and then was it Tom Grigg who looked at it for a while, and then he got farther and found some information, and then at that, and like he wrote down everything, you know, and then where he was stuck, and that was when Martin stepped in and said, you know, oh, you know, no, I see a better way to fix this, right? So in the end, it was Martin that fixed it and not us, but all of this investigation and writing work that we did was, you know, was not wasted, because it got the bug to a point where an expert could look at it and either point us in the right direction or submit a fix themselves. So that's like a, it's like, well, what do you do if you fail, right? And so I hope that people know that, you know, if they fail, they shouldn't just give up. Like, you open a pull request with, write down everything about how far you got. And then at that point, when an expert sees that you've done that, they'll know that they're not wasting their time on someone who's flailing, you know, that they can give really targeted advice. It's something I used to always say in my Scala 2, how to be a Scala 2 contributor talks was, half-baked PRs are okay. You know, like if you, however far you get, write it up, submit a PR and ask for help. That's far more likely to get expert help than just sort of randomly saying, hey, can anyone help me?
Yeah, in general, it's a good idea to save your work and to publish it in an appropriate form, to, as you say, to attract attention, to get help, because if it's on your machine, nobody can see it. And then the chances are that in the process of writing it down, you might also get new insights.
Yeah. Yeah, and even if you didn't produce a fix yourself, that doesn't mean you failed. You made valuable progress that enabled someone else to take it over the finish line.
Yeah, exactly. Great. So thank you everyone for coming. I'll upload this this video to YouTube, and hopefully we can make more videos in the future like that. So, and thank you, Dale and Seth, for sharing also your experiences. You shared, I think, a lot of valuable tools to get started. I'll tag them also on YouTube so that there is a little list. And have a great week, everyone. I'll see you during the next spree.
Thank you very much.
Thanks.
Nice work. Huh?
Thanks. Bye-bye.
Thanks.
Thanks. Bye.